This is part 3 of topic 4, and in this topic we're looking at game theory. Now, the first game that we're dealing with is prisoner's dilemma. So we've got two suspects. They have been caught committing a robbery, and the police have grabbed them, taken them to the station and put them in separate rooms. Now, assuming that they didn't have an opportunity to talk to each other and negotiate some sort of deal before they got grabbed by the police and taken away, they've got two strategies. They can either confess to the crime or not confess to the crime. Now, the payoffs that we see here are in the payoff matrix. So the idea is, if they are separated, put in separate rooms, and both suspects do not confess, then the police have enough evidence on them to put them away for, say, 1 year. So they've got a little bit of evidence that they were going to commit this crime, but not a lot. However, if they both confess that they were actually going to undertake some serious crime on this property as they were breaking into it, then they both get 6 years. So that they are relatively realistic payoffs. If suspect 1 does not confess, but suspect 2 confesses, suspect 1 gets put away for 15 years. And suspect 2 gets off free. Now, presumably, if we're in the upper right-hand quadrant here, it means that suspect 2 has actually made a deal with the police to confess on suspect number 1, to put number 1 away, and suspect 2 gets off free. The bottom left-hand corner is actually suspect 1 that has made a deal with the police. So then, the next question is, what is the Nash equilibrium? How do you actually play this game? Well, when you're actually trying to work out the solution to games like this, the first thing that you should be doing is trying to find a dominant strategy. So a dominant strategy is one which is better for you regardless of what the other person does. So if there is a strategy that always gives you a better payoff than an alternative strategy, that is a dominant strategy. So looking at this payoff matrix, let's have a look at suspect 1. If they confess, they get either 0 or 6 years. If they do not confess, they get either 1 or 15. So in this case, confessing is a dominant strategy, because if you confess, you will get 0 years in prison rather than 1 if suspect 2 does not confess, and by confessing, if you're suspect 1, you will get 6 years rather than 15 years if suspect 2 confesses. So your jail time by confessing is always less than if you don't confess. The same sort of logic with suspect 2. Now, it always makes sense to actually play your dominant strategy in a game like this, and the dominant strategy is confess, confess. And so we're in a situation where the solution to the game, by following the dominant strategy, is 6 years and 6 years for each prisoner. That's why it's so difficult for both prisoners to actually hold out in a situation like this. It's very difficult for them both to not confess, because if they don't confess but the other person does, they get 15 years. So you really do want to avoid that 15-year possibility. So 6 and 6 is the solution to the game. Now, a Nash equilibrium is a situation where, or a part of the payoff matrix where no individual wants to change their strategy once they hit that point. So let's assume that we are in this 6-6, the confess-confess quadrant of this game. Then you've got to ask yourself, do either of these suspects have an incentive to change their strategy? Okay, and we have to actually get at the idea of Nash equilibrium, we have to analyze this one matrix, one person at a time. Okay, so does either person have an incentive to change? Well, the answer is no. If the game lands in the bottom right-hand quadrant, suspect 1 gets 6 years. Would they want to then change their strategy? Suspect 1 changing their strategy means they go from 6 years to 15 years by changing their strategy from confess to not confess. Would suspect 2 want to change their strategy? Well, suspect 2 currently is getting 6 years. Would they want to change their strategy? Well, if they go from confess to not confess, then the game moves over here from 6 to 15. So that doesn't make sense for suspect number 2. Don't worry about how they could actually go from confessing to unconfessing. You might look at that and think, well, that's not possible. That's not relevant. In defining and working out a Nash equilibrium, we have to assume that that can be done. So by looking at this bottom right-hand quadrant and saying there's no incentive for suspect 1 to go from 6 to 15, there's no incentive for them to go from for suspect 2 to go from 6 to 15, then we are basically concluding that the bottom right-hand quadrant is the Nash equilibrium. So that's how game theory works. The next game, we've got 2 cruise ship companies. They are looking at a particular cruise and they're trying to work out whether they will charge high prices or low prices. Now, $450 and $350 for Royal Caribbean, that's the ticket price. The payoffs are profits for the cruises in millions. So top right-hand quadrant, we've got a profit of 350 million, profit for Royal Caribbean, 275 million for Carnival. Okay, so outside the box, we've got ticket prices in dollars. Inside the payoffs, we've got profits for the cruise we're looking at in millions. And so these 2 companies have to work out what ticket prices they will charge for an upcoming cruise. Now, this is a simultaneous game. So these 2 companies have to actually set their ticket prices without knowing what the other company is going to set their prices at. So to solve this game, we first look for a dominant strategy. So that is a payoff which is always better for one of the companies. So let's have a look at Royal Caribbean first. If they set 350, they earn 320 million or 175 million. But if they set 450, they earn 350 million or 50 million. Now, Royal Caribbean does not have a dominant strategy because if Carnival sets a price of 450, it would be optimal for Royal Caribbean to set a price of 450. However, if Carnival sets a price of 300, it would be dominant for Royal Caribbean to set a price of 350. So for Royal Caribbean or Caribbean to actually maximize profits, it's actually dependent upon what Carnival does. So let's have a look for a dominant strategy for Carnival. If they set a price of 300, they earn profits of 375 million or 185 million. Now those profits of 375 and 185 under a price of 300 are always better than the profits they would earn of 275 and 60 million if they set a price of 450. So we are assuming in this game that both companies know the prices that the other companies are thinking about setting approximately, and the profits that would be earned by the opposing company if either ticket price was set. But what we don't know is, or what the companies don't know, is which option the other company is going to select. So both companies know what the payoff matrix looks like here, but they don't know which strategy these 2 companies are going for. But Royal Caribbean can work it out. If Royal Caribbean knows that as a result of these ticket prices, the profits will be approximately what they are in this payoff matrix, then Royal Caribbean will know that Carnival has a dominant strategy of $300 because that will earn them $375 rather than $275. Carnival, that is, and 300 will earn Carnival 185 million rather than 60 million. So Carnival will always make more profit by charging 300. So Royal Caribbean knows that the left-hand column of this game is basically ruled out. Carnival will never set a price of 450 because 300 is the dominant strategy. So given that, Royal Caribbean knows that it has an option of either profit of 175 or 50. The profit of 320 and 350 for Royal Caribbean is not available. The left-hand column has been ruled out. So Royal Caribbean will pick between 175 and 50. They will pick the 175, therefore they will charge a price of $350 per ticket. Next game is Renegade discounting. Coke and Pepsi. With Coke and Pepsi, very often you see them discounting their product. It's out the front of the store, it's out the front of Coles or Woolworths whenever you go in there, and it's at the front of one of the aisles, and it's quite heavily discounted. The discount lasts for a little while, and then the price goes back up to a higher level. So what I've got here is a payoff matrix, high prices and discounted low prices. Now, if both maintain high prices, they will earn profits of 12 and 13 respectively. If, however, they get into a price war and discount their prices, they will earn 6,300 and 8,000 respectively. So obviously they don't want to get into a price war, a permanent price war. It's too costly in terms of their profits. Now, the next question is, well, which part of this matrix does Coke prefer? Coke prefers the upper right-hand quadrant because they will, if they set a low price and Pepsi maintains a high price, Coke earns 16. But Pepsi's not going to live with the $9,000 profit under that particular set of strategies. So if Coke, let's assume that the game starts off with high prices. If Coke tries to increase its profits by lowering its price from 13,000 to 16,000, then Pepsi is quickly going to get sick of that because their profit would have decreased from 12 to 9. They are probably going to discount as well and take the game down to the bottom right-hand quadrant. After a while, Coke will probably agree with Pepsi to start charging high prices again to move back to the upper left-hand quadrant. Pepsi obviously prefers the bottom left-hand quadrant for the same reason. They would prefer 14,000 rather than 12,000, but if they stay there at the discounted prices for too long, the game will end up going back to the lower right-hand quadrant, low prices. They'll be into a price war, and they'll both be harmed by that. Okay, so there's actually three Nash equilibria in this game. The first two are the top right and the bottom left. So if you have a look at that, the top right is a Nash because once the game's there, you need to ask yourself, is there any incentive for Coke to change its strategy? No, it would be lowering its profit from 16 to 13. Is there any strategy for any incentive for Pepsi to change its strategy? No, it would be changing from 9 to 6,300. But that makes sense if the game is played just 1 or 2 periods. But if it's an ongoing game, then if Coke somehow gets to this top right-hand quadrant by cutting prices, even though that is a Nash equilibrium in a static sense, in a dynamic setting, it won't be, because even though Pepsi has no incentive in the short term to actually lower its profits from 9 down to 6,300, by cutting its prices too in response to a price cut by Pepsi, it'll actually be forced to Pepsi will have to cut prices as well and take the game down to the bottom right-hand quadrant in a multi-period version of this game, in the hope that eventually high prices will be restored and their profit can go back up to 12,000. Okay, so we've got two Nash equilibria. The final Nash equilibria is on the final slide here, and it's actually a very complex Nash equilibrium. And I'm going to go through this just to show you how complex game theory can actually become, because in standard textbook you go through Prisoner's Dilemma and it looks quite simple, but it can actually become quite complex. Now you don't have to, you won't be expected to reproduce this game in any exam setting, so this is not examinable. It's simply an exercise for us to go through just for now to illustrate how complex game theory can actually be. Okay. The other Nash equilibrium here is called a mixed strategy Nash equilibrium. Okay, so let's imagine that we start off high. If one company cheats and undertakes price discounting and stays there, we know that the other company will respond to cut prices as well, even though that will incur a loss for them in the short term because they want to get back to high. So if we start off at high and Coke cuts and we go to the top right hand quadrant, then Pepsi will incur losses through a reduction in profit down to 6,300 for a period so that they can actually get back to high prices. Now if you were Pepsi and Coke cut their prices and grabbed some extra profit, and you were then forced to cut your prices to take to reduce your profit further down to 6,300. Remember, your Pepsi. How long would you stay down there in a price war? How many periods? Would you go back to the top right? The top left-hand quadrant, high immediately? If you do, the problem with that is that you are giving Coke no real incentive to, depending upon the payoffs, you're giving them little incentive to actually stop cheating on you. Okay, so one option would be to, if Coke cuts its price and stays there for too long, you could actually punish them by cutting as well and taking them down to the bottom right hand quadrant for as long as it takes for the profit that they made in the top right hand quadrant to be wiped out, the extra profit to be wiped out, and then agree with them to charge high prices again. Okay, so that would be a threat. So in this game, Coke needs to be very careful. It needs to lower its price, but then come back to a high strategy. So start at 13,000, cut its price, earn the 16,000, but then come back. It needs to be careful that it doesn't discount for too long, because that will just mean that Pepsi starts discounting for too long and both companies will spend too much time in the bottom right hand quadrant. So the optimal strategy here for Coke is to discount, come back, discount, come back, but not to over discount in the sense of staying at low prices for too long. Pepsi's strategy at the same time is to discount and go from profit of 12,000 to 14, but then come back, discount and come back quickly. So you discount for a week, then you come back to high prices for a month. You discount for a week, you come back to high prices for a month. Now, the whole idea behind this is that discounting, first of all, encourages more people to try your product, so you may attract new customers, and it's also trying to grab some of the other companies' market share as well. So if you go in Coke and Pepsi, you want to buy some sort of cola drink and Pepsi's on special, but you're normally a Coke drinker, then if Pepsi's on special, you may be more tempted to try it. And if you try it, you may like it more and become a permanent consumer of it, in which case Pepsi, through its discounting, would have grabbed you as a consumer. Or you may be a new consumer, but just be attracted by the temporarily low price, and then you become a permanent consumer. So the final equilibrium is one where Coke discounts and comes back, discounts and comes back. The same with Pepsi, it discounts and comes back. As I said before, discount for a week, come back to high prices for a month. Then you do it again. You discount for a week, come back. But you've got to be very careful as one of these companies that you don't over discount. Because if you over discount, then you'll force the other company to over discount, and you'll be spending too much time in the bottom right hand quadrant. At the same time, you don't want to under discount, because if you under discount and don't spend enough time with your prices at discounted levels, you won't be generating as much, or you won't be generating as benefits which are large enough from the discounting process. So you won't be enjoying the maximum amount of benefits that you possibly could from the discounting process. So what I've got down here, and this is the final part of this puzzle, are two equations, one for Pepsi and one for Coke. And these equations work out, given these payoffs, the proportion of time that these two companies should spend at high and low prices. So let's have a look at Pepsi's situation here on the left. Coke's decision-making process is here on the right. So for Pepsi, we're over here. Pepsi wants to set up a discounting strategy, which means that Coke has the same expected profit payoff, or the same expected profit, under high prices and low prices. So Pepsi wants to set up its discounting routine so that Coke has the same expected profit under either high or low prices. So if it can do that, Coke has no incentive to charge high prices continually. It's got no incentive to charge low prices continuously, because Coke would be earning the same profit under both scenarios, high or low prices. So how does Pepsi work this out? Well, what we've got here on the left-hand side of this first equation, I've got Pepsi sets P so that P is equal to the proportion of time that Pepsi sets high prices. Therefore, P minus 1 is the proportion of time that Pepsi sets low prices. And P works out to 45.5%. So under Pepsi, we've got an equation here. On the left-hand side, this is actually the expected profit of Coke when it sets high prices. The expected profit of Coke when it sets high prices. How do I know that? Well, the payoffs here are 13,000 and 10,500, which are the payoffs in this matrix when Coke sets high prices. And so when we multiply P by 13,000, we're really saying that when Pepsi maintains high prices, then Coke's payoff will be 13,000 times the percentage of time that Pepsi actually sets those high prices. So when Coke sets high prices, its expected profit is going to be this left-hand side of this first equation. So when Coke sets high prices, it will expect to be earning 13,000 for 45.4% of the time, and it will expect to earn 10,500 for 1 minus P, which is 54.6% of the time. Now, when Coke sets low prices, it will earn either 16,000 or 8,000. Once again, the way I've set this up, the right-hand side of this equation is the expected profit to Coke of setting low prices. 16,000 times P, which is 16,000 times the proportion of time Pepsi sets high prices, and 8,000 times 1 minus P, which is 8,000 times the percentage of time that Pepsi sets low prices. So by setting up the equation here, what I've actually got is on the left-hand side, the expected profit to Coke of setting high prices, and on the right-hand side I've got the expected profit to Coke of setting low prices. The idea is P is selected, the value of P is selected to equalize the two sides of this equation, to make this equality hold, and P comes out to be 45.4%. So if Pepsi spends 45.4% of its time charging high prices and 54.6% of its time charging low prices, then given these payoffs, Coke will be indifferent between high and low prices, and so then Coke will have no incentive to over discount. So Coke will likely play the strategy of high prices for say 2 or 3 weeks, then discount, then come back, discount, then come back, discount, then come back. Okay, Coke does the same. Coke sets up the equation on the right-hand side, which doesn't give Pepsi any incentive to over discount and stay at low prices for too long. Okay, so that's the science behind this final game. The idea is we want both companies to be able to discount and then come back, discount then come back, but we don't want them spending too long in the low discount situation, because if they do, then both companies will tend to over discount and both of them will set low prices and stay in the bottom right hand quadrant for too long, and that will harm both companies. So by following these equations, we can work out the optimal times that they should spend at high and low prices so that they can enjoy the benefits of low prices but not over discount, causing a price war.